All right, everyone. Welcome back. Maybe. Uh, so today we'll be solving the Russian Winter Camp 2019 problem number one, which is an organic synthesis problem, and it's all in Russian, but I've already translated the question for you. So, uh, here we have this scheme, and we have so many structures. We have Q, so many. Look at how many we have to draw. Of course, I've attempted this problem before, and it's actually kind of fun. Actually, it's really fun, this problem. Okay, so we need to draw A to Q, and then now the other questions we'll just have a look later. Let's finish the scheme first. So let's look at our starting product. We treat it with a strong base and an allyl-bromide. Of course, this is your classic SN2 moment. This proton is abstracted because it has the least pKa. So let's draw our product. So it's a 5-membered ring with that coming out, and then what's next? It's the COET group. COOME or ET? Or it's Me. And then your carbonyl on that side, and then your allyl group. There you go. 1, 2, 3. Yes. Okay. Here's the structure for A. Then you treat it with ozone and zinc in acetic acid. That is, of course, reductive ozonolysis. So it's going to cleave this double bond and turn it into a carbonyl. Great. Then we treated this with this compound and Hansch ester with L-proline as a base. And we are given a clue that this Hansch ester reduces the Novanago product. So we know that this is a Novanago condensation reaction because it's given to us. So what's happening here is that this enol, it's going to attack our carbonyl right here, this aldehyde right here, and then just attacks like so. So that will be, I'm sorry, that should be an oxygen. OH right there. So it's gonna be something like that. So let's draw our product. Let me duplicate this real quick. And OH, yes, and then let's draw, actually I'll put it on this side because the 5-membered ring is gonna be bulky. One like that. That's our 5-membered ring. Let me redraw that. You know, I'm very addicted to when if the structure's not good enough, I have to redraw. I don't know why. Sorry about that. It's gonna take up so much time. Okay, so there's our 5-membered ring, and this will be our carbonyl. Actually, this should be an oxygen, right? Oxygen and our, there you go. That's our product, and the Novanago condensation will eliminate this hydroxyl group and form this double bond. But it is given to us that the Hansch ester reduces this double bond, so let's take that away. Okay, here's our product C. Then we treat it with TF2O and 2,6-lutein. That, of course, will turn our carbonyl into an enolate, a triplet enolate. Now there's a reason why this specific enolate or this specific carbonyl is turned into a triplet enolate. It's because you see we have 2 carbonyls. I mean, let's go back to the structure. We have 2 carbonyls, and this proton is hella acidic. It's way more acidic than this proton. It's way more acidic than this proton if we compare, because we have 2 carbonyls. So this is why. Then D to E, we treat with chromium 2 chloride and nickel 2 chloride. This is the Nozaki-Yamakishi reaction, and it's kind of like a Grignard reagent. It's kind of like Grignard, whereby we turn this carbon as like a kind of we can think of this carbon acting as a nucleophile and attacks this carbonyl, so it's kind of like Grignard. So it's gonna be a 6-membered ring, and the OTF group is gone. So it's going to be like this. Let me redraw that quickly so that it will look aesthetically pleasing. CMOA group, let's move that right over there. Our 6-membered ring. Now for this question, stereochemistry is not required, so that's good, because there are so many diastereoselective steps in this synthesis. And that's our OH right there. Next to our OH, we have our 5-membered lactone, right? It's called a lactone, right? Lactam is the amide. There you go. Now this 5-membered ring looks a bit ugly. There you go, looks good. And then the double bond will go here. Actually here, right? It goes here, right? I think it goes right there. Yeah, I think so. Yeah, I think it goes there.
Yeah, มันไม่เป็นเอาอ่ะ
Then after we treat it with the Nozaki Hiyama, E to F, we dehydrate the alcohol. It's a classic dehydrating reagent. So we dehydrate that here. No question of selectivity of the dehydration. F to G, we treat it with osmium tetroxide, so it will of course add to these 2 carbons. Okay, great. And then H, we treat it with hydrogen. So of course that's going to add to our double bond right there. Good. H2I, we treat it with sodium periodate. Sodium periodate. Sodium periodate is a classic reagent for a 1,2-diol cleavage, and it will cleave into a carbonyl. So our product will be something like so. This will be our product, and if you add a potassium permanganate to it, it will also oxidize it into a carboxylic acid. But we only have sodium periodate here, so there's no worry about that. Then we treat it with ethylene glycol in the presence of an acid. So that of course will be protection of our aldehyde right here. So it's going to be something like this. Okay, we treat it with formaldehyde with a slightly acidic environment. So the thing about formaldehyde is that now we treat it with formaldehyde. It can go both ways. One, it can add to this carbon. It is an aldol. This reaction is an aldol condensation. It's an alpha beta. It's aldol, but the thing is we have 2 sites that we can choose. We have this hydrogen right here. We have this hydrogen right here, right? Thing is, it selects. It has selectivity over. It selects the ketone over the ester. Why? The reason is that this oxygen right here resonates with this carbonyl. And just think about like these 2 this system is like kind of just hanging out on its own. Like, you know, we can resonate, we're good, we're stable. And if we deprotonate this and then we add this bond to the resonance, it's kind of like, oh, now we like are kind of disrupting the structure that can already resonate. But for the carbonyl right here, this ketone right here, we cannot resonate with anything, right? This carbonyl cannot do resonance with any other nearby atoms right here. So this ketone is kind of like waiting on, like, hey, when's my turn to share my, like, flow my electrons. And so this ketone will receive our carbonyl. Oh, what's happening? It's kind of buggy. Oh shit. I don't know what's happening, so let me just draw over here. So I don't know what's happening right there. Right there. And our OH group. Nice. K2L. K2L will be, this is an Apple reaction. A classic Apple reaction. Now, normally you would see CCl4, CBr4 as our Apple reagent. But, I2 is also a valid Apple reagent. You can also use I2s in Apple reactions and get the same product as you would expect. Of course, Apple reactions turn our hydroxyl group into a better leaving group, and then replace it with our nucleophile. In this case, it's iodide. M. We treat it with tributyl tin hydride and AIBN. That is, of course, a halogen abstraction using radicals. So that will get our iodine away using radical abstraction, and you will be left with this product. Let's see. N. We treat it with HCl and HCl. Of course, that is the protection of our acetal. Remove that. Add back the carbonyl. Then we treat it with this really funky reducing reagent under hexafluoroisopropanol. Now, there's a reason why we have to use this reagent, and you will see. Now, if we calculate the double bond equivalence of O, you would get that 15 times 2, which is 30. 30 plus 2 is 32. Minus 22, that's 10. 10 divided by 2 is 5. The double bond equivalence for this compound is 5. So, how many double bond equivalents we have in N? We have 1, 2, 3, 4, 5, and 6. So only one carbonyl is being reduced by a reducing agent. And it's going to be this carbonyl. Why? Because, of course, we all know aldehydes are more reactive than ketones. So, of course, it's going to be reduced first. Now, if you notice, let me draw this hydride structure. So it's BH, right? Connected to 3. Oh, that's quite a strange group. Very specific reducing reagent. CF3, CF3, OCF3. Oh, sorry, forgot to draw another carbon. O, CF3, CF3. The reason that we have to use a specific reagent because we need to lower the electron density on the hydride bond as possible, so that it would not reduce our ketone, so that it will not reduce here. So it would only select this aldehyde. So that's why we have to use such a specific reducing reagent. Then we treat it with, again, our Apple reaction, our Apple. So we turn that OH into iodine. Now we treat it with, I love radical reactions. Can't tell you how much I love radical reactions. Samarium to iodide. Now, samarium to iodide will do a single electron transfer. It will do a set on our ketone, and it will leave us with our, and it will leave us with a this radical, and then this radical can react intramolecularly with the iodine, so it will become like so. Actually, it should. There you go. So it will become something like this, and then it will form our 5-membered ring, like so, because it's an intramolecular radical cyclization. So, oh, my battery's too low. And so we will have a leftover hydroxyl group right there. And then our methyl group right here. It's way too close. Let me just... There you go. And that should be our final product Q. And then for question number 2, this question asks us, why do we need to use such a specific reducing reagent? Why can't we use sodium borohydride, NaBH3CN, or NaBH triacetate? Well, of course, the reason is for aldehyde selectivity, we need to use this specific reagent so that it will reduce only the aldehyde, because all the other borohydrides will reduce the ketone too. We have to make the reducing reagent as weak as possible so that it will not reduce anything further. Now 3 requires us to draw the mechanism for D to E. D to E is the Nozaki-Hiyama-Kishi reaction. So let me draw the reaction real quick. So it starts off with our reaction, I'm just going to draw a simplified version. So it starts with Rx and Rx. Let's label the R1X, and then our R1X will do an addition. We'll do an addition to the nickel. So the nickel will be here, nickel 0. Let me move up so that it will be more beautiful. So our nickel 0, and then we will add the R1X to the nickel, so that will be an oxidative addition right there. So now this nickel is +2. Then chromium will come in. Chromium 3 will come in. And where do we get our chromium 3? That will be next. Now chromium 3 will come in. Now we initially start off with chromium 2, right? Now chromium 3 will come in from the formation from this transformation. So 2 of the chromium 2 plus will be oxidized into chromium 3 plus, and then this chromium 3 plus will transmetallate with our complex. So it will become this complex, which is just transmetallation, because we swapped our metals from nickel to chromium. And then this reagent just reacts with our carbonyl, maybe let's say an acetone right there, reacts with our acetone to give us our product, which will be something like that. And then after workup, you get our product. There you go. That's the mechanism from D to E, which is the Nozaki-Hiyama-Kishi reaction. Let me write it out. Nozaki-Hiyama-Kishi reaction. It's kind of like it's similar to Grignard, and I actually kind of dig this reaction. It's really cool. It uses 2 of our transition metal complex, and I think it's quite cool, don't you think? So yeah, that's it for our problem solving today. Quite fun. So many compounds you have to determine and go through. And yeah, that will be our synthesis for today. Thank you for watching.